Sine and cosine. Objectives. Find function values for the sine and cosine of the special angles. Identify the domain and range of sine and cosine functions. Use reference angles to evaluate trigonometric functions. Evaluate sine and cosine values using a calculator. The unit circle. The unit circle has a center at the origin 0, 0 and a radius of 1. In the unit circle, the length of the intercepted arc is equal to the radian measure of the central angle T. Here is the unit circle with our special angles marked. Here I have pi over 6. Well, I can count around the unit circle by pi over 6. Here is 1 pi over 6. Here is 2 pi over 6, which is also pi over 3, which is what that simplifies to. I have 3 pi over 6. Well, 3 pi over 6 simplifies to be pi over 2. Then I have another pi over 6. That's going to be 4 pi over 6 is my 2 pi over 3. Another pi over 6 is going to get me to 5 pi over 6. And yet another is going to get me to 6 pi over 6, which simplifies to be pi. We continue this way around the unit circle. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. The next way we could divide up the unit circle is by quarter pi's, pi over 4. So we see here pi over 4. That's pi over 4 radians to get to that terminal side. So if we count by pi over 4, we have pi over 4. Another pi over 4 would give us 2 pi over 4, which is pi over 2. Another pi over 4 would give us 3 pi over 4. Another pi over 4 is going to give us 4 pi over 4, which is pi. And we continue around. 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4, which is 2 pi. Another way to count around that unit circle is by third pi's. So we can start at our pi over 3 radians. And if we add another third pi, that would be 2 pi over 3. We add yet another, that's 3 pi over 3, or pi. Then 4 pi over 3. Then 5 pi over 3. And then 6 pi over 3, which is the 2 pi. Another way to count around is by half pi's. So our first half pi is to there. So that'd be 1 pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and 4 pi over 2, which is my 2 pi. So it's simply a matter of breaking up the unit circle into those different denominations. We can use the unit circle to find different trigonometric functions. So let x, y be the endpoint on the unit circle of an arc of length s. The xy coordinate of this point can be described as functions of the angle. For any angle t, we can label the intersection of that terminal side and the unit circle by its coordinates x, y. So the coordinates x and y will be the outputs of the trigonometric functions. F of t equals the cosine of t, and f of t equals sine of t, respectively. This means that x is the cosine of t, and that y is the sine of t. Defining sine and cosine functions from the unit circle. The sine function has an input that is the measure of the angle and an output that is the y-coordinate of the corresponding point on the unit circle. The cosine function has an input that is the measure of the angle and an output that is the x-coordinate of the corresponding point on the unit circle. Here we can see this xy point. Directly, x is the value of cosine t, and y is the value of sine of t. We do not always need to write these functions with parentheses. Sine of t is the same as sine parentheses t, and cosine t is the same as cosine parentheses t. Likewise, cosine squared t is a commonly used shorthand notation for cosine of t all squared. Be aware that many calculators and computers do not recognize the shorthand notation. When in doubt, use the extra parentheses when entering calculations into a calculator or a computer. Now it is good to note, and we'll see this again later, that cosine squared t equals the cosine of t squared, but it is not the same as cosine of t squared. A certain angle t corresponds to a point on the unit circle at negative square root 2, square root 2, as shown in the figure. Find cosine of t and sine of t. We know that the cosine of t is equal to the x part of that point. So that is going to be the negative square root of 2 over 2. And sine of t, again, we don't have to write that with a parenthesis. Sine of t is going to be equal to the y part of the coordinate, square root of 2 over 2. Let's find cosine of 90 degrees and sine of 90 degrees. 90 degrees is going to take us right here on the unit circle. That coordinate is 0, 1. So the cosine of 90 degrees is 0. The input is the angle, and the output is the x part of the coordinate. Sine of 90 degrees equals 1. Again, the angle is the input, and the output is going to be the y part of the coordinate on the unit circle. Let's find the cosine and sine of the angle pi. So here they've used the full words. We can go ahead and use our notation, cosine of pi. Where is pi? Pi is right here, and it has the coordinate of negative 1, 0. So we know that the cosine of pi is negative 1. And the sine of pi is 0. The Pythagorean identity. Now, you're familiar with the Pythagorean theorem. The Pythagorean theorem says that squaring the legs of a triangle, a right triangle, and then adding them is going to be equal to the square of the hypotenuse. So the Pythagorean identity in trigonometry is similar, except for x, we are replacing that with the cosine of t. Instead of x squared, we'll have cosine squared of t. And likewise with y squared, it is replaced with sine squared of t. And since we're on the unit circle, then the hypotenuse is 1 and 1 squared is 1. If sine of t is equal to 3/7 and t is in the second quadrant, find cosine of t. Well, if we start this, we have the cosine squared of t plus, normally I would put sine squared t here, or sine of t all squared, but I know that the sine of t is 3/7. So this will be 3/7 here squared equals 1. Now I need to solve for cosine of t. So when I do my squaring, I get cosine squared of t plus 9/49 equals 1. Then I have cosine squared of t equals 40/49 after subtracting 9/49 from both sides. Now I take the square root. Don't forget your plus minus. I have the cosine of t now on the left side. On the right side, I have plus or minus. Square root of 40 is going to simplify down to 2 square roots of 10. And the square root of 49 simplifies to 7. So I have two values here, but we've been told that we're looking for t in the second quadrant. First quadrant here, second quadrant over here. Now, x is going to be positive over here, but x will be negative over here. Similarly, cosine will be positive over here, but it'll be negative over here. So I'm going to want to choose the negative 2 square roots of 10 over 7. So my cosine of t in the second quadrant is equal to 2 square roots of 10 over 7. That is the negative choice. If cosine of t is 24/25 and t is in the fourth quadrant, find t. So a similar problem, but we don't have a picture this time. It's okay, we can still use the Pythagorean theorem. I have cosine squared of t plus sine squared of t equals 1. Now I'm going to replace cosine of t with 24/25, but in the formula that is squared. Finish out with the rest of the formula. Sine squared t equals 1. Then I'm going to go ahead and square my fraction. 24 squared, 576, over 25 squared is 625, plus sine squared t equals 1. Then when I subtract 576 over 625 from 1, and make sure that we keep that in a fraction form, I get 49 625ths. Now, taking the square root, I'm going to have sine of t is equal to plus or minus square root of 49 is 7, square root of 625 is 25. Now I'm looking in the fourth quadrant. So if t is in the fourth quadrant down here, I know that my cosine is positive, but my sine is negative. This means I'm going to need to select the negative 7/25. So sine of t in the fourth quadrant is going to be negative 7/25. An angle's reference angle, T prime, is the measure of the smallest positive acute angle T formed by the terminal side of the angle T and the x-axis. Let's look in the different quadrants. For an example here, I have T equals 38 degrees. Now, the reference angle is going to be the smallest measure that takes to get back to the x-axis. So I could go either back down 38 degrees, or I could go this way to 142 degrees, but the smaller angle is 38 degrees. So you can see here that T prime is 38 degrees. And so it goes with all angles in the first quadrant. T prime is going to be the same as the angle T. In quadrant 2, let's say that I have 142 degrees. Well, the quickest way to get back to the x-axis, that's what we're looking for, we would either go this way, 38 degrees, or we'd have to go back this way 142 degrees to be able to get to the x-axis, and the smallest positive acute angle to get there would be the 38 degrees. So it turns out that T prime is equal to pi minus T, or 180 degrees minus T if we're working in degrees. Next, I'm in quadrant 3. If my angle is T equals 218 degrees, I could either travel back 38 degrees to get back to the x-axis, or I could go back this way 142 degrees to get back to the x-axis, but the quickest way would be to go 38 degrees this way. So our T prime is 38 degrees. And in fact, for quadrant 3 angles, T prime is always T minus pi, or T minus 180 degrees if we're in degrees. Now for quadrant 4, let's say I have some angle T of 322 degrees, which lands my terminal side in quadrant 4. I can either go this way 38 degrees to get back to the x-axis, or I could go backwards this way 142 degrees to get back to the x-axis. And of course, 38 degrees is going to be the shortest way to get back to the x-axis. So 38 degrees is my T prime. So in that quadrant, T prime is going to be equal to 2 pi minus T, or 360 degrees minus T, in order to find your reference angle if you're in degrees. Find the reference angle T prime. If T equals 225 degrees, I like to write here the quadrantal angles. Since we're in degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees, and 0 degrees or 360 degrees. I know 225 lies in here. So I really just need to figure out, if I've traveled this far, how far is it to get back to the x-axis? So I need to subtract off 180 degrees. So t prime is going to be 225 degrees minus 180 degrees. That gives me a t prime of 45 degrees. If t is 5 pi over 3, then again, I can count through the unit circle. This is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and 5 pi over 3 is about right there. So I'm in the fourth quadrant. I just need to know how much further do I have to go to get to the 0 radians or the 2 pi radians. So that's going to be just one more pi over 3 would get us to 6 pi over 3. So t prime is going to be pi over 3. Finding the sine and cosine of special angles. Let's look first at 45-degree angles. This would also be pi over 4. So when I look at that on the unit circle, I know that xy is the same as xx, meaning that the measure of x and y are the same. So I can use my Pythagorean theorem. I know that x squared plus y squared equals 1 squared. And since my x is equal to y, I can replace my y with an x. And now I have like terms to combine. This gives me x squared equals 1/2. When I take the square root, I get x equals plus or minus the square root of 1/2, which is plus or minus 1 over the square root of 2. And I'll rationalize that to get plus or minus the square root of 2 over 2. Now, I know in the first quadrant here that both x and y are going to be positive. So this xy coordinate is going to have an x of positive square root of 2 over 2. And the y is going to be the same as the x. So it is also square root of 2 over 2. This means that the sine of 45 degrees is equal to the square root of 2 over 2. And the cosine of 45 degrees is also the square root of 2 over 2. Here I have the angles that have a reference angle of pi over 4 plotted. Let's go ahead and find the cosine and sine values for each of those angles. The cosine of 3 pi over 4. Well, I know this distance here is going to be the same as this distance here. It's just that we're on the other side of the y-axis. So I know that the value, the absolute value of that is going to be the same. It's going to be the square root of 2 over 2. But because we had to go left to get to this point, it's going to be a negative square root of 2 over 2. The sine is still going to be the square root of 2 over 2. You can see the height of those points is the same. Now the cosine of 5 pi over 4. Here we are down here. Now I know that the x distance this way is the same as the x distance this way. but we had to move to the left. So that means that I have a negative square root of 2 over 2 for my cosine. Also, this height is the same as this height, and this height is also the same as this height. It's just that we had to go underneath the x-axis to get there. That means that our sine is going to be a negative square root of 2 over 2. Now let's look at 7 pi over 4. Again, the x is the same as the pi over 4, so the cosine is going to be the same. It's going to be the square root of 2 over 2. And for the sine of 7 pi over 4, we had to move down below that x-axis, so I know it's going to have a negative value of negative square root of 2 over 2. Now let's take a look at a 30-degree angle. With a 30-degree angle, this height is 1/2, so I know that my y is 1/2. I can use my Pythagorean theorem. X squared plus y squared equals 1 squared, and try and solve for my x. So x squared plus 1/2 squared equals 1. That's x squared plus 1/4 equals 1. So x squared equals 3/4. Now when I take the square root, I'll have x is plus or minus the square root of 3 over the square root of 4, which is 2. Now, when I'm in the first quadrant, I know I had to move to the right to be able to get up to this point. So that's going to be a positive square root of 3 over 2. There's my coordinate. This means that the cosine of 30 degrees is equal to the square root of 3 over 2. And the sine of 30 degrees is going to be equal to 1/2. So let's practice here finding the cosine and sine values for each of the angles listed. You'll notice I have pointed out here the angles that have a reference angle of pi over 6. So they're all going to have the same cosine and sine values for the angles. It's just going to depend on what quadrant they're in, whether the sine is positive or negative, or the cosine is positive or negative. So when I'm looking at 5 pi over 6, I'm over here in the second quadrant. So I'm going to have a cosine of square root 3 over 2, but it'll be negative since I had to move to the left to get there. And the sine is going to be the same as for the pi over 6, so that's 1/2. I'm looking at 7 pi over 6. The cosine is, again, we had to move to the left, so it's going to be negative square root of 3 over 2. And now we had to move down to get to that point, so the sine is going to be a negative 1/2. Cosine of 11 pi over 6. 11 pi over 6 is over there. We can see the cosine is going to be the same as for pi over 6. So the cosine is a positive square root 3 over 2, but the sine is negative 1/2 because we had to travel down to get to that point. Now taking a look at 60-degree angles, I have over here my x is most definitely 1/2. Now I can use my Pythagorean theorem, and the x being 1/2 substituted, I'm going to have 1/4 plus y squared equals 1. So y squared equals 3/4, and y is going to be plus or minus the square root of 3 over 2. All right, so I know that the cosine of 60 degrees is 1/2, and the sine of 60 degrees is a positive square root of 3 over 2 because I had to travel up in order to get to that point. Now you might be having a little deja vu at this point because these values seem familiar. We just did 30-degree angles, so when I have a 30-degree here, this is going to be 60 degrees. And when this is 60 degrees, that's going to be 30 degrees. And so the values for cosine and sine for 30 degrees and 60 degrees just flip-flop. But you can be assured that 1/2 is always going to be paired with a square root of 3 over 2. Over here, we have square root of 3 over 2 first, and the 1/2 is the height of the point where that terminal side intersects the unit circle. So let's find the cosine and sine values for each of these angles listed. And of course, again, the angles that are listed have a reference angle of pi over 3. So we know that the cosine and sine values are going to be the same, the absolute value. So this is going to be 1/2. This is going to be the square root of 3 over 2. And that's the same all the way around. Now we just need to decide when we're at 2 pi over 3, I know that the cosine is going to be negative and the sine is positive. When I'm here at 4 pi over 3, I know the cosine is negative and the sine is also negative. And at 5 pi over 3, the cosine is positive this time, but the sine is negative. Now it's important to know the values of cosine and sine of these special angles. Here I have the angles in the first quadrant in radians and degrees, and I have these quadrantal angles. So if you understand and can remember the cosine and sine values of these, and you can understand how to use reference angles, you'll be able to give the coordinates or the cosine and sine values of all of those special angles around the entire unit circle, which is really nice. It really simplifies what you have to remember. So this chart is a good thing to print out and maybe keep with yourself to quiz yourself, but don't just try and memorize the chart. Try and think through what the unit circle looks like and where you land on the unit circle by moving over a half and up, or moving up a half and over. And then it's a lot easier to commit these things to memory that way. So let's practice finding the values here, not by finding them in the unit circle, not by using a calculator or by looking them up in a chart, but by using your knowledge of reference angles and the signs of the sine and cosine functions in each of the 4 quadrants. So let's look at cosine of 315 degrees and sine of 315 degrees. Remember, I'm in angles, so I'm going to mark my quadrantal angles so I can determine what quadrant I'm landing in, and it looks like we're landing somewhere over in here. So my reference angle is going to be how much more it takes to get right back to the x-axis. So how much more than 315 degrees does it take to get to the x-axis, and that's going to be a t prime of 45 degrees. So this means 45 degrees is our reference angle, and I know that in that quadrant that the x's are positive and the y's are negative. So this means that the cosine of 315 degrees is going to be positive, and the sine of 315 degrees is going to be negative. And I think about just that reference angle of 45 degrees, and the value for cosine is square root 2 over 2. The value for sine is square root of 2 over 2, but I've already set that to be a negative for that fourth quadrant. Now let's work a problem in radians. Again, it's good to know what quadrant we're working in. I'm here at negative pi over 6. Negative pi over 6. So it's actually just 1 pi over 6 that would take us back to the x-axis. So my t prime is a positive pi over 6. But here in that fourth quadrant, we know that the cosine is positive and the sine is negative. So the cosine of negative pi over 6 is going to be positive, and the sine of negative pi over 6 is going to be negative. And think about that reference angle t prime being pi over 6, and on the unit circle the cosine is square root 3 over 2. The sine is 1/2, but I've already set that to be a negative, so the sine of negative pi over 6 is a negative 1/2. Now let's give the coordinates of the point on the unit circle at an angle of 5 pi over 3. Again, it helps just to picture what quadrant we're in. If I'm going to divide this by thirds, I'm not even going to put the y-axis on there. So this is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and 5 pi over 3. You know, it would take just one more pi over 3 to get back to the x-axis. So that is my reference angle, pi over 3. Except that in 5 pi over 3 we're quadrant 4, and I know that the sign is going to be positive, negative in there for those coordinates. So my coordinate is going to be a positive here and a negative here. But as far as the absolute value, it's going to be the same as it is for the reference angle pi over 3. So my x to get to that pi over 3 point is 1/2, and the y is going to be square root 3 over 2. We've already set it to be a negative, and so then that gets us down to this over here, this negative square root of 3 over 2. Now here in your notes is a kind of a blank template of the unit circle, and it's a really good idea to regenerate this many times and practice drawing it and labeling everything so that you can learn all of the angle and radian measures and the coordinates of each of those terminal points. So I'll just get you started. This is the point 1, 0. And I know this is 0 radians or 0 degrees. And here at this next point, I know that I have gone up 1/2 and what pairs with the 1/2 but square root 3 over 2. And the degree measure here is 30 degrees, and the radian measure is pi over 6. And you can go around and complete each of these with the information we've gone over in the lesson, and you can verify those with your unit circle handout, and that'll be a good way for you to practice and commit this to memory. This is going to be some of the most used information that you'll need to have handy at any moment in your next several math classes. Using a calculator to find sine and cosine. To find the cosine and sine of angles other than the special angles, we'll use a computer or calculator. Just be aware that you need to make sure your calculator is in radian mode if you're inputting radians, and that it's in degree mode if you're inputting degrees. Let's evaluate cosine of 3.7. That is in radians. Remember, with the absence of a degree symbol, it is assumed that this is radians. We're going to do this using a scientific calculator. All right, the first thing we'll do is check the mode, and I can see my mode here says degree mode. I need it in radian mode. So find your mode button and just move that over to where the radians is selected and quit so that you're going back to the home screen. Now I'm going to go into my trig menu and select cosine, and I'll input 3.7, and I get approximately negative 0.848 is what I'll round that to. And let's evaluate the sine of 22 degrees. I do want to show you something here. If you're in radian mode, you can still do this problem. Go into your trig menu and select the sine. You can put your 22. If you leave it like that, your calculator is going to assume it's radians. So what you can do is go into your angle menu and input degrees. That way your calculator knows for sure that this is a degree measure, and this is telling us that the sine of 22 degrees is approximately 0.375. Let's go ahead and do this again, but by changing our mode. Let's change the mode to degree mode and try this again. Trig menu. I'm going to take the sine of 22. This time I don't need to put the degree symbol because I am in degree mode, so the calculator understands that I'm putting in a degree measure. And then when I hit enter, I get the same as if I did the sine of 22 with the degree symbol and had it in radian mode. Now just one more time. Let's change the mode back to radian mode. And let's try taking the sine of 22, but we leave it at that. We don't put a degree sign, so we're in radian mode. We don't put a degree sign. The calculator is going to interpret this to mean 22 radians. And when I hit enter, I get a very different value than I did when I put the degree symbol there in radian mode. So just to be aware that you have your calculator in the correct mode when you're doing these problems. Identifying domain and range of sine and cosine functions. What are the domains and ranges of the sine and cosine functions? Now, by examining the unit circle, we can discover this answer. Now the domain, this means what kind of angles can be inputs of the function. Range, that's what kind of outputs will we have for those functions. We can see that the domain is negative infinity to infinity because we can put negative angles in. It's always going to be coterminal with some positive angle that's between 0 and 360 degrees, or 0 and 2 pi. And if we have some angle that is many revolutions, it's okay. It's still going to be coterminal with some angle that's between one full revolution. And the range, you'll notice all of the outputs that we had, they were between -1 and 1. The lowest we could go was -1, and the highest we could go was 1. So our range for the sine and the cosine functions is -1 to 1.